All right, so this morning we're going to start with integral test. We're also going to do direct comparison and limit comparison. Now, we're going to see that in these tests, you don't have to use them. And as a matter of fact, the integral tests, I would suggest you don't use. But why do we need to use them? Well, first of all, in some cases, the integral test is something you have to use. So if there's no other test to do, integral test has to be done. Or there could be an AP test that requires you to do the integral test. So they could say, using the integral test, determine if this diverges or converges. So you might know the answer. So like in part A, we know the answer. We know that's a harmonic series, and we know that harmonic diverges. So we can say, ooh, A diverges by the P-series test. But if they're asking specifically for the integral test, you won't get the credit because remember, AP is looking for the work to support it. So that's why we have to use this or know how to do this integral test. So please know that I did not write this box stuff. I stole this from somebody. I did not come up with this mnemonic. But if F is decreasing, continuous, and positive, so that's the first thing that has to happen. So dogs cuss in prison. Whatever, you won't forget it. For X is greater than 1, and then for some function, then what's going to happen is the sum and the derivative are both either going to converge or diverge. Now, you're going to know it converges if your integral is going to go to a number. You're going to know that it diverges if your integral goes to infinity. So it's kind of like that chapter we did with integration by parts, and we did the integration to infinity. We're going to practice those again, and this is sort of like a recap of that kind of stuff. But remember, we did say that if it equaled a number, then that was just our answer. If it equaled infinity, it diverged. So this is kind of pulling that back in. So looking at number 1, this does not mean that the series converges to the value of the definite integral. So if your answer is 1/2, that doesn't mean that you're converging to 1/2. It just means that it is converging. You would have to do a whole other series of events to find out what the actual sum was. And this is, again, not a horizontal asymptote or anything like that. Note 2, the function need only be decreasing at some point beyond k. So at some point, you've got to start decreasing. We aren't going to have an issue with that. And again, if the AP test is asking you to solve using the integral test, well, then it is going to be decreasing, continuous, and positive. It's just that as you go up and up in calculus, and for example, if you're a math major and you're doing modern algebra, which is an entire proofs class, those are the kinds of things that you're going to have to focus on. You would have to show and prove that it was decreasing, continuous, and positive. Okay? So let's look at A. We know that if n is equal to 1, this thing is continuous because it's going to be discontinuous if n is equal to 0. But that's out of our domain, so we don't have to worry about that. It is getting smaller and smaller and smaller. 1/2, 1/3, 1/4, 1/5, 1/6, 1/7. Smaller and smaller and smaller. It is positive as well. There's no negative going on in here between 1 and infinity. So we fulfill all of this. Now, keep in mind, you know that this diverges already. Because of the P series, P is equal to 1, okay? And it is a harmonic, which is going to diverge. So if I was asking you whether this thing diverged or converged, and I didn't care how, then you would already have your answer and you'd be done. But if I said you have to use the integral test, then this is what you would have to do. You have to set up the integration right here. So you're doing the integration from 1 to infinity of 1 over n dn. Now, how do we do that? Let's go back and think about 2 chapters ago. This is in the B position. Remember A and B? So you're going to do the limit. And yes, you have to write the word limit down as b approaches infinity of the integration from 1 to b of 1 over n dn. Okay? So you need to take the integration of this. So if you integrate 1 over n, you end up with ln n. Now, this is where a lot of you dropped off the limit. You can't drop off the limit. You have to write the word limit again of ln of n from 1 to b. Okay? Now, for those of you who kept the limit at this point, you dropped off the limit now. You still can't drop off the word limit. We are going to plug in the b, we are going to plug in the 1, but the limit has to be there because you still have a b in your equation, and we still need to be able to plug that infinity in. Okay? So we end up with the limit as b approaches infinity of ln of b, where you plug in the infinity, minus ln of 1. Well, now we know ln of 1 is just equal to 0, so that's gone. Ln of infinity, well, remember your graph, ln looks like this. So as you're going to infinity, this thing, while slowly, is going to get bigger and bigger and bigger, which means it's going to infinity. Now, we said right up here, if your limit as b approaches infinity goes to infinity, your equation will diverge, which we knew in the first place. So we know we've got the right answer. We know we've done it correctly. Okay? But remember, if AP asks specifically for integral test, you have to do the integral from 1 to infinity. Okay? All right, let's look at B. So for part B, we've got n over n squared plus 1. So, got to integrate from 1 to infinity of n over n squared plus 1 dn. All right, so let's go ahead and write our equation. We have the limit as b approaches infinity of the integration from 1 to b of n over n squared plus 1 dn. So U-substitution. I'm going to make the u, this denominator, n squared plus 1. du dn is equal to 2n. So I'm integrating n over u times du over 2n, where my n's cancel. So I'm integrating 1/2 the integration of 1 over u du. Make sure you remember that using the denominator. It doesn't just pop up to the numerator. So it's going to be 1/2 ln of u. So we've got the limit as b approaches infinity. Don't forget that limit of 1/2 ln of u, which is n squared plus 1, evaluated from 1 to b. So we need to keep the limit written down, limit b approaches infinity of 1/2, and we're going to plug in the b, of ln of b squared plus 1 minus, plug in the 1, 1/2 ln of 1 squared plus 1, and that's going to be ln 2. Okay? So, looking right here, ln of b squared plus 1. Well, it's very similar to ln of b. I've now squared the b and I'm adding 1 to it. So I'm doing infinity squared plus 1. This thing is still going to infinity. I understand that this is a number, but remember, if you have $1 billion and you take $1 away, who cares? You still have almost $1 billion. So this thing is going to infinity. Okay? Infinity, take away a little bit, isn't going to change anything. So you're still diverging. Now, if we look up here, we're going to be doing 2 other things today. We're going to be doing something called direct comparison test, which is not my favorite either, and then limit comparison test. Limit comparison test is one that I like. You also did it in math analysis. It's one that you're going to see a lot. This is kind of looking like if we were to mimic this equation of n over n squared and get rid of that plus 1, it would be like 1 over n. Well, if we reduce that to be 1 over n, isn't that just a harmonic series which diverges? So it's kind of going to do the same type of thing as the harmonic series might do. And like I said, we'll look at that once we get into direct comparison and limit comparison tests today. Okay? But just sort of keep that in the back of your head. Again, the only time I'm doing integral test is if someone says you must do integral test, or unless there's no other possible test to do. when we start recapping and doing all of these together, there is going to be one instance in like 20 that we're going to have to do integral test. Again, we kind of stay away from it because, as you can see, it's a whole lot of work when some of the other ones, like the P series, is a little bit faster. Okay? All right, let's look at C. Now again, if you're looking at C, if we're just thinking intuition, this is kind of like 1 over n squared. I mean, if you ignore this plus 1, this thing's probably going to act like 1 over n squared, where P is equal to 2. Well, if P is equal to 2 and P is larger, we know that that thing converges. So my guess is that this thing converges. So I know that you're not getting multiple choice on the AP test, but you are going to get some multiple choice on my quizzes and things. And looking at that, if I had to guess, I would say that this thing is going to converge without doing any work at all. But let's go ahead and do some work and see what we get. So we're doing the integration from 1 to infinity of 1 over n squared plus 1 dn. All right, so the limit as b approaches infinity of 1 to b of 1 over n squared plus 1 dn. Now, you would think that this thing is a U-substitution. I'm going to write it. You probably shouldn't. Oh dear, running out of lead. All right, hold on. Sorry, out of lead. Okay, my point was not to write this down because it's not going to work. All right, so if I have u is equal to n squared plus 1, I've got du dn equals 2n. Well, look, I don't have an n to actually cancel. So this isn't going to work. So this isn't U-substitution. Well, remember when we were in class. Oh, miss you guys. Remember when we were in class, I said the very first thing you want to do is you want to try U-substitution. If U-substitution doesn't work, your next step is going to be to look at those inverse trig functions. If inverse trig functions doesn't work, you then look at integration by parts, integration by partial fractions, so on and so forth. So we've exhausted, number one. Number one is that U-substitution doesn't work. So then we go to inverse trig. Well, there's that plus sign in the denominator. So plus sign looks like a t, so we think inverse tan. So this is an inverse tan function. So we've got the limit as b approaches infinity of the inverse tan of n. We want to evaluate that from 1 to b. So I have the limit as b approaches infinity. Notice I'm writing the word limit every single time. And now I'm going to plug in the b. Tan inverse of b minus tan inverse of 1. Okay? Now, I can plug in the infinity. Where does tangent go to infinity? Well, the first place tangent goes to infinity is up at the top, pi over 2. Or down at the bottom, negative pi over 2. I'm going to stick with pi over 2. Where does tangent equal 1? Well, tangent equals a 1, the first place at pi over 4. So essentially you have pi over 2 minus pi over 4. Now here's the deal. You could come up with a final answer, but I know that this is going to equal some sort of a number. Okay? If it equals some sort of a number, we said, oh, that converges. So therefore, we know that this will converge. Okay? Which is what we suspected in the beginning when we thought that P was 2 and P would converge. So if you are just saying whether you think something converges or diverges, you can use anything you want. But if they ask specifically for some sort of a test, you have to write it all down. All right, let's look at part D. Part D, again, we've got the integration from 1 to infinity of n e to the negative n squared. All right, so, looks ugly. Let's go ahead, limit. B approaches infinity of 1 to b of n e to the negative n squared. Now, I know a lot of you I'm like, oh, do we have to write all of these things down? And the answer, of course, is yes. Remember, it's all in the work. You can't skip all of these little steps. Even if you know what's going to happen, even if you know where you're going, you can't skip these steps. And looking at this doesn't look like anything I would know. I wouldn't be able to guess whether I was thinking this thing would diverge or converge. Okay, so we've got to do the work. So, our u is negative n squared. Du over dn is equal to negative 2n. So I'm integrating n e to the u, du over negative 2n. Well, the n's go away. And I'm integrating negative 1/2 e to the u. All right, so limit as b approaches infinity of negative 1/2 e to the u, because the integration of e to the u is e to the u. Oops, no du, we already integrated. I'm having trouble. 1 to b. So we're plugging in b and 1. So we have the limit as b approaches infinity of negative 1/2 e to the negative b squared minus a negative 1/2 e to the negative 1. All right, so if you're plugging in infinity, you've got e to the negative infinity, which is 1 over e to the infinity. Well, that means your denominator is really big, and this thing is going to 0, which means your final answer is going to equal a positive 1/2 e to the negative 1. Now, that's not a variable. E is 2.7, so this is 1/2 times 1 over 2.7 to the 1. So that's going to be a number. Well, since it equals a number, this thing will converge. Okay? So that is the integral test. You get to practice some of those on your homework. Let us move on to the next one. The next one is the comparison test. Now, direct comparison. Again, not quite my favorite, and I'll tell you why. It's not that it's hard, because it's just kind of like the limit comparison test. The deal is, though, that you have to memorize a couple things that I just never really memorize, and you have to look at something afterwards that I don't really like to look at. So again, direct comparison, not going to be my choice. If they say I have to use direct comparison, fine, I'll use direct comparison. But unless they say it, I'm probably not going to use it. Again, not that it's hard, and we actually need to go over it because it helps us do limit comparison. But at any rate, let's just take a look at it. All right, so direct comparison. If a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0, okay? Now, what are they talking about, a sub n and b sub n? We'll get there. We'll talk about what that is. If b sub n, the sigma, as n approaches infinity of b sub n converges, and a sub n is in between 0 and b sub n, then a sub n is going to converge as well. So what you were trying to show is you want to show that the original function, the one that they give you, is less than or equal to the new function. Okay? So essentially, you want to say that the original function is smaller. If the original function is smaller, then it's going to do what your new function does. And you're like, what? New function? We'll talk. We'll talk. Don't worry. You'll get it. All right, now this one says, if a sub n diverges and a sub n is between 0 and b sub n, then b sub n will diverge. What you're actually doing now is you want to show that your original is greater than or equal to your new one. So your original is larger. Okay? And again, right here, this step is what bothers me. And when we do limit comparison test, which we're already getting to 20 minutes, so we'll probably do limit comparison test tomorrow. But once we do the limit comparison test, you're going to see that it's way easier than trying to figure out which one's bigger and which one's smaller and blah, 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 blah. So let's go ahead and get started with these. Now, remember yesterday, or whenever you watched that other video, it always said to start with the nth term test. So let's just go through and pretend, because now we've got the nth term test, the geometric test, we've got the integral test, we've got, and the p-series test. We've got 4 tests under our belt already. So let's try the limit comparison, or the nth term test, the nth term test limit to derive. Now, if you do the limit as n approaches infinity, this thing is going to 0. That means this test is failing. The test fails. So you can't do that. So that meant that you needed to do another test to determine whether this thing was going to diverge or converge. Well, now looking at this test, or this function, what does it look like? Doesn't it look like a p-series? Think back to when we were doing p-series, and I don't actually know, I think I have a p-series somewhere around here. If you're looking back at your p-series, remember 1 over n cubed, where p was equal to 3. Well, notice in all of these p-series problems, I don't have any pluses or minuses, numbers. I don't have any numbers being multiplied. There really aren't any numbers in a true p-series. Well, interestingly enough, for direct and limit comparison, p-series, geometric series, those are the ones that we tend to use the most in a comparison, because this isn't an exact p-series because of this +1. But it is kind of like a p-series. It's like 1 over n cubed, where p is equal to 3, which we know will converge. Okay? So what we're going to do is we're going to compare it to 1 over n cubed. Okay? So I'm thinking that I'm comparing this thing to 1 over n cubed, and I'm thinking that since p is equal to 3, it converges. Well, since I'm thinking it's converging, I have to come up here and I have to show that the original function is less than the new function. So I need to show that my original function is less than or equal to my new function. Now, I need to think about this in order to prove that. Let's just make n equal to 1. If n is equal to 1, this is going to be 1 over 2. And this one's going to be 1 over 1. Well, 1/2 is less than 1. All right, well, let's pick another number. Let's pick 2. I'm staying small because we want to make sure that this is equal. Well, we're staying small because we want to make sure that we don't have huge numbers here. So let's try 2. Well, this is 1 over 9, and this is 1 over 8. Well, 1 over 9 is smaller than 1 over 8. Now, I'm not going negative, because take a look at my domain. I'm going from 1 to infinity. So I don't have to worry about the negative numbers. I'm just looking at those positive numbers. So this is, in fact, smaller. Well, since the original is smaller than the new one, then you can say, by direct comparison test, 1 over n cubed plus 1 converges. So it's going to converge because your p-series converged. You were showing that by the direct comparison test, this is the statement that AP is going to be looking for. They're going to be looking for the thing that you said, that the original is smaller than the new one. Okay? Now, what if? Just doing a what if here. What if my function was 1 over n cubed minus 1? Okay, so let's say that up here it was 1n cubed minus 1, and it's still looking like 1 over n cubed, where p is equal to 3, and I'm thinking it converges. Well, if I show this, and I plug in some numbers, don't plug in a 1, that doesn't work, because if you plug in a 1, that's undefined. So maybe we plug in a 2. So this is going to be 1 over 7th, and this is going to be 1 over 8. 1 over 7 is not smaller than 1 over 8. So what would happen is this would have a test fails. Now, it doesn't mean that you can't do anything. It doesn't mean you can't figure out it converges or diverges. It just means that you have to do a different test. So you have to do another test. And really, the limit comparison test would be a better one in this case, which we will learn tomorrow. Again, though, direct comparison, I'm only going to do if I am told to do so. All right, so let's go through this second one. 1 over 3 to the n plus 2. Now, again, it's that plus 2 that's throwing us off. So what I'm going to do is I'm going to say, all right, this is kind of like 1 over 3 to the n. Does that look familiar to you from our last thing? It's not a p-series, because p, we have those numbers and the exponent, and that's not that. We can't do the nth term test, because if you do the limit as n approaches infinity, this thing is going to 0, test fails. What about geometric? If you were to do 1 over 3 to the n, you're going to get 1 over 3 for your first term, 1 over 9 for your second term, 1 over 27 for your third term. Your r is equal to 1 over 3. Interesting. Now, if your r is 1/3, look at that little sheet that tells you all the different things about whether p is bigger or smaller and r is bigger or smaller. If your r is smaller, that means that it is going to converge. So if your r is smaller, it's converging. Okay, so we're thinking that this thing converges because of this function right here. Now that we've added 2 to it. Now again, we've got to show that our original is less than or equal to our new one. So we're going to plug in some numbers. If you plug in a 1, you've got 1 over 5. Is that less than 1 over 3? Yes, it is. If you plug in a 2, 3 squared is 9, so that's 1 over 11. Is 1 over 11 less than 1 over 9? Yes, it is. So, by the direct comparison test, 1 over 3 to the n plus 2 converges because it fulfills what we said right here. Our original was less than our new. That's what this statement was saying right here. Okay? This statement is just saying that your original function is less than your new function. This statement right here is just saying that your original function is greater than your new function. That's where the a and the b are coming into play. I think it's easier. Instead of doing a and b, it's original and new. Way easier to think about. Okay? All right, so let's do another one. P-series or geometric? Oh, my phone thought I was talking to it. I'm going to go with, this is like 1 over n to the 1/2, where p is equal to 1/2. So I'm thinking that this thing is going to diverge. Just like a p-series would diverge, I think this one's going to diverge. Well, we look up at the top. If it's diverging, it says we need to show that our original is bigger than our new one. All right, so our original, 1 over the square root of n minus 1, is greater than or equal to our new one. Now notice when I wrote the new one, I went ahead and I just wrote it as the square root of n, not n to the 1/2. I wrote it as n to the 1/2 so I could get the p. All right, plugging in a 1 gives us an undefined thing, so let's plug in a 4. I don't want to plug in a 2 because the square root of 2, yuck, don't know it. So if I'm plugging in a 4, I've got 1 over the square root of 4 minus 1, so that's a 1/3, right? And then this one, I have 1 over the square root of 4, which is 2, 1/2. 1/3 and 1/2. So, is that working? Let's, like 1/3 is not bigger than 1/2. So let's look at another one. So if we plug in a 9, if you, did I do it right? Show that your original is larger. Our original one is larger. Yeah, so this one's not working. So since this one's not working, hold on, just double checking. If we plug in a 9, we've got that square root of, oh, I was doing 4. See, I had to think through my problems. It's hard to do it when you're on video and not in the classroom. If I plug in a 4, the square root of 4 is 2, and 2 minus 1 is 1. So this is 1 over 1, which is greater than 1/2. If we plug in a 9, the square root of 9 is 3. 3 minus 1 is 2, so that's 1/2, which is greater than or 1/3. All right, yay, there we go. I'm like, wait a minute, this thing is supposed to work. So that is what happens. Don't forget to take the square root when you're plugging in your numbers. So yes, by the direct comparison test, 1 over the square root of n minus 1 will diverge. Okay? All right, why don't you try and do D? See if you can go ahead and do D, and I will walk you through it. Push pause. All right, let's take a look. So this one is like 1 over n to the 4th, where p is equal to 4. So I'm going to say converges. Okay, so I think this is going to converge. I just want to make sure. So let's see now. Look, everything so far has worked. Even part C that we were having issues with, but it did work. So since this one converges, we have to show that the first one, the original, is less than or equal to the new one. Now, n to the 4th. You can go ahead and plug in a 1. A 1 is probably the easiest because 1 to the 4th is 1. So you get 1 over negative 9 is less than or equal to a 1. Well, 1 is bigger than negative 1 over 9. Let us go ahead and plug in a 2. I just want to see this. If we plug in a 2, we've got 1 over, well, let's do alpha y equals 1 over 2 raised to the 4th minus 10. And then the second one, we've got 1 over 2 to the 4th. So you've got that 1/6 is less than or equal to 1/16. So our 1 didn't really work. Our 1 didn't give us our right answer because we still had a negative right there. And 1 was bigger than a negative 1/9. But look at here. 1/6 is not smaller than a 1/16. 1/16 is smaller than 1/6. So if you get this negative number and you're plugging in with that 1, you got to be super careful. Notice in all of these we've checked a couple different numbers. So this is not going to work. This is not a direct comparison. Because right here, 1/16 is not bigger than 1/6. So in this case, we couldn't use direct comparison. You would be able to do a limit comparison, which again, like I said, we're already at 33 minutes, so we'll go ahead and push that to tomorrow. So tomorrow we'll do the limit comparison. Now I do believe on your homework, let me double check, you have, I know you have the integral one. You have 3 integral ones and you have 2 direct comparison. Go ahead and do those 5, and then tomorrow we'll pick up, I'm looking at our calendar, tomorrow we'll do limit comparison, which will go kind of fast, and then we've got alternating ratio and root. We'll probably have to push a little bit, but on Friday we can do a little bit more with our combination of all. So we'll just sort of push them out and we'll do them as we can. We've got enough time. All right. Have a great day, guys.